Welcome back to the deep dive. If you've been in tech for, well, any length of time, you know that keeping a network secure can feel like
Mhm.
patching a million tiny leaks constantly.
It really can. And the jargon alone is overwhelming.
Exactly. IDS, IPS, SIME, it's a lot. So our mission today is pretty straightforward. We want to cut through that noise. We're going to analyze the core systems that really defend networks today.
Moving way beyond that old idea of just a simple firewall at the edge.
Miles beyond it. So where do we start? I guess with the evolution of defense itself.
That makes sense. The sources point to a big shift away from standalone defenses towards these integrated platforms.
You mean things like Unified Threat Management, UTMs, and next-generation firewalls, NGFWs?
Precisely. That's the first major architectural change we need to unpack. These aren't just slightly faster packet filters.
Right. The sources stress that. A UTM, for instance, it tries to consolidate pretty much everything, doesn't it? Anti-spam, intrusion detection,
VPN, application control, web filtering, the whole lot, potentially in one box.
which sounds great on the surface, like
Yeah.
management simplicity, right?
It does sound great, but there's a flip side. That simplicity, well, it introduces a potential operational headache.
How so?
Consolidation is easier to manage, sure, but it also creates this massive single point of failure. If that UTM box goes down,
Then everything goes down.
mhm,
VPN, detection, prevention, the works.
exactly, everything's offline. So organizations are constantly doing this balancing act. Do you go for the management ease of a UTM?
Or the resilience you get from deploying specialized, separate systems for each job.
Right. There's no single right answer. It's all about trade-offs and your risk tolerance.
Okay, that makes a lot of sense.
Yeah.
So whether they're integrated or standalone, what are these systems actually trying to catch? The sources seem to put threats into two main categories.
Yeah, basically the known versus the unknown, or as the sources put it, exploits versus anomalies.
Okay, define those. An exploit is.
An exploit is an attack we already know about. It has a known pattern, a signature. Think of it like a fingerprint. Your defense system is programmed to look for that specific fingerprint.
Simple enough. But the other one, the anomaly, that sounds trickier.
It is. An anomaly is any kind of unusual network behavior.
Yeah.
Maybe CPU usage on a server suddenly spikes way higher than normal.
Or network traffic volumes just go completely off the charts compared to the usual pattern.
Exactly. It's a deviation from the norm. And that's crucial because an anomaly might be the first sign of something completely new.
The zero-day attack.
Precisely. The attack that exploits a vulnerability the developers haven't even discovered yet, let alone had time to patch.
So 0 days warning for the defenders.
Right. Since there's no signature, no fingerprint to look for, your only hope is spotting the weird behavior it causes on the network.
Which explains why so much focus now is on behavioral analysis, not just signature matching.
It's a fundamental shift in defense strategy. You have to baseline normal to spot abnormal.
Okay, let's dig into some specific threats. Denial of service, DOS, always a major concern for keeping things running. How do systems spot those?
Well, DOS is tough because attackers can use various protocols, TCP, UDP, ICMP, even SCTP. They're not limited.
So the defense system needs to look for patterns across protocol.
Yes. The sources highlight four main indicators. First, just a really high volume of traffic using one specific protocol.
Okay.
Second, you might see sweep or scan attempts, the attacker trying to map out your network's open ports before launching the main attack.
Reconnaissance.
Right. And third and fourth are related. A large volume of traffic coming from a single IP address or a large volume going to a single target IP.
But spotting those spikes. I see the sources really hammer this point.
Yeah.
You need an accurate baseline of what normal traffic looks like first.
That is the absolute crux of the problem for anomaly detection, especially for DOS. You have to know what normal is.
And getting that wrong is dangerous.
Extremely. Set your thresholds too high and the attack is already underway, maybe succeeding before the alarm bells ring.
Set them too low.
And you're buried in false alerts. Security teams get alert fatigue, start ignoring things, or worse, the system might start dropping legitimate traffic because it thinks it's an attack.
So establishing and constantly updating that baseline of normal behavior is a huge ongoing task.
It's the hidden, constant workload behind effective DOS defense and anomaly detection in general.
Let's look at another protocol-level attack.
Yeah.
The SYN flood. Classic TCP attack. It feels almost elegant in its nastiness.
It really does exploit the protocol beautifully from the attacker's view. It targets the standard TCP three-way handshake, SYN, CHEC, ACK.
Right, the normal start to a connection.
Normally, the server sends the SONET back to the client and reserves a little bit of memory in its connection table, waiting for that final ACK.
But in a SYN flood,
The malicious client sends floods of initial SYN packets, but it never sends the final ACK to complete the handshake.
so the server's table fills up.
Fills right up with these half-open connections, thousands of them. Eventually, it runs out of space in that table.
And it can't accept any new connections from legitimate users.
Exactly. The service effectively goes offline. Availability just drops to zero.
Brutal. Okay, shifting gears from availability to attacks, aiming for control buffer overflows. How do network defenses spot signs of those? I mean, the overflow itself happens inside the server's memory, right?
It does, but the attempt often leaves clues on the network. The goal is always to overwrite data, hoping to inject and run malicious code.
So what are the network signs?
Network defense systems look for things like HTTP requests with unusually large bodies or just a ridiculous number of headers attached.
Trying to stuff too much data in.
Pretty much. Trying to exceed whatever buffer size the server application allocated for handling that request. Other signs can be things like malformed or illegal host names and requests, or even trying to use weird, non-existent HTTP versions like HTTP 0.9.
Why that?
Because sometimes those edge cases aren't handled properly by the server code and can trigger the vulnerability the attacker wants to exploit.
Okay, so these behavioral signs, these anomalies, lead us directly to the big players in detection and prevention, IDS and IPS. Let's start with the IDS, Intrusion Detection System, the passive one.
That's right. Think of the IDS as the lookout. Its primary job is to detect unauthorized access or suspicious activity and then raise an alert.
It doesn't stop the traffic itself.
Not directly. It might suggest an action, like telling a nearby firewall to update a rule, an access control list, or ACL. But the IDS itself is mostly about observation and alerting.
The sources use a good analogy. The firewall is like the security guard at the door, checking IDs based on the list.
Yeah, deciding who gets in based on policy and the IDS.
It's like the security camera system inside, watching everything, spotting suspicious behavior the guard might miss, and radioing it in.
That's a great way to put it. Captures the passive monitoring aspect.
And these IDS systems, they collect data in different ways, right? Host-based versus network-based.
Exactly. You have NIDs, network-based IDS, which monitors traffic flowing across the network. It often uses a network card in what's called promiscuous mode to just passively listen to everything going by.
And HIDs.
Host-based IDS. That's installed on the individual computer or server you want to protect. It looks at local data system logs, file changes, running processes on that specific machine. Two different perspectives.
Okay, so how does either type actually decide if something is bad? We mentioned signatures and anomalies earlier.
Right. Those are the two main detection methodologies. First, signature-based detection. That's pure pattern matching. Does this packet or sequence of packets match a known attack fingerprint?
Like the exploit definition we talked about.
Exactly. This can get quite sophisticated using stateful matching to look for patterns across multiple interactions, not just a single packet.
But the big weakness is
It can only catch what it already knows. If there's no signature for a new attack, like a 0 day.
it sails right past.
Correct. Which brings us back to the second method, anomaly-based detection.
Looking for deviations from that crucial baseline of normal behavior.
Yep. Using statistical analysis, looking at traffic volumes, or checking if network packets actually conform to the rules of their supposed protocol. For example, does this DNS packet have fields that shouldn't exist according to the DNS standard? That's anomalous.
And this is the key for catching 0 days.
It's the primary hope, yes. But it comes with that significant trade-off we discussed.
False positives. Because defining normal perfectly is really, really hard.
Extremely hard. So anomaly detection systems are often tuned carefully to balance sensitivity against the noise of false alarms. They can also look for higher-level attack patterns, like signs of cross-site scripting, XSS, or SQL injection attempts in web traffic.
Okay, so if the IDS is the camera system alerting on suspicious activity, then the intrusion prevention system, the IPS, is more like the guard who can actually tackle someone.
That's a good way to think about it. The IPS is the proactive layer. It doesn't just detect an alert, it actively intervenes. It can drop malicious packets outright, it can terminate suspicious network connections, it can reset TCP sessions. Going back to the SYN flood example,
An IPS could actively kill off those half-open connections.
it could be configured to drop TCP handshakes that remain incomplete for too long, directly mitigating the attack's effect.
But this power comes with a big string attached, doesn't it? The sources emphasize deployment, and IPS has to be in line,
Absolutely critical point. All the network traffic you want to protect must flow directly through the IPS device. That's how it can inspect and block in real time.
which means if it makes a mistake, a false positive.
It immediately blocks legitimate traffic. A user trying to do their job suddenly gets cut off because the IPS misidentified their traffic as malicious.
That sounds like a nightmare for operations teams. Performance bottlenecks too, I imagine.
Definitely. Inspecting every single packet adds latency. But yeah, the impact of false positives is the biggest concern with IPS. Blocking legitimate business activity is a serious problem.
So tuning becomes even more critical for an IPS than an IDS.
Much more critical. Best practice says you have to be way more conservative with IPS rules that block traffic. Be very sure before you drop something. An IDS can afford to be a bit more aggressive with alerting because an alert doesn't break anything itself. An IPS block does.
Okay, that clarifies the distinction really well. Detection versus active prevention and the risks involved. Now, let's look at some of the more sophisticated tools that help manage all this complexity. Starting with the zero-day problem again, the sandbox.
Ah, yes, the sandbox. It's really the security industry's answer to the fact that traditional signature-based antivirus just can't keep up with brand new malware.
So what is it exactly?
It's basically a safe, isolated environment, often a virtual machine that's completely walled off from your real network and system.
And you use it to run suspicious stuff.
Exactly. You take that untested file, that weird email attachment, that dodgy link, and you execute it inside the sandbox.
Where it can't do any real harm if it is malicious.
Right. The sandbox environment is heavily monitored. If the code tries to make weird network connections, modify critical system files, encrypt data basically, if it behaves like malware.
The sandbox sees it, flags it as malicious, even if no antivirus signature exists for it yet.
Precisely. It's behavioral analysis specifically for unknown files and code, essential for catching those zero-day exploits or brand new malware strains.
And deployment can be a physical box, cloud service.
All of the above. It can be a dedicated appliance, a module within a UTM, a local VM setup, or increasingly a cloud-based service where you submit files for analysis.
Very clever. Okay, let's switch gears to another massive problem, spam. The sheer volume is mind-boggling. Sources estimate over 95% of all email is spam.
It's an insane statistic, but widely cited, 95% or more. That filtering challenge is immense.
We know about blacklists blocking known bad senders and whitelists allowing known good ones. But the sources mention something called gray listing. That sounds interesting.
Gray listing is quite clever because it leverages how legitimate mail servers behave versus spam bots.
How does it work?
When an email arrives from a sender the filter hasn't seen before, gray listing temporarily rejects it. It sends back a try again later type of error message to the sending server.
Okay, why?
Because legitimate mail servers are designed to handle temporary failures. They'll queue the message and automatically try sending it again after a few minutes.
Ah, but spam bots.
Spammers are usually playing a numbers game. They blast out millions of emails as fast as possible. If one gets a temporary failure, they typically don't bother retrying. It's not worth their time or resources.
So if the sending server does retry successfully after that initial rejection,
The gray listing filter assumed it's probably the legitimate server, allows the email through, and adds the sender-recipient pair to a temporary whitelist so future emails get through immediately.
that's really smart. A low-cost way to filter out a lot of lazy spamming.
Very efficient for certain types of spam, yes.
Okay, now let's move up the stack. We have all these systems, firewalls, IDPs, sandbox, spam filters generating logs and alerts. We need something to make sense of it all. Enter the SIEM.
Right, the Security Information and Event Management System. This is the big correlation engine.
It combines two things, right? SIEM and SIM.
Exactly. Security Event Management, which is the real-time monitoring and correlation of alerts as they happen, and Security Information Management, which is the long-term storage, analysis, and reporting of all that log data.
But the real magic, the sources say, is the correlation.
Absolutely. That's a core value proposition of a SIEM. It's not just a log bucket. It ingests data from everything, firewalls, servers, antivirus, applications, databases, you name it.
And then it connects the dots between seemingly unrelated events.
Precisely. It joins log records together based on common attributes like the same IP address, username, or timestamp to build a bigger picture of what's happening.
Can you give an example?
Sure. Maybe the SIEM sees 50 failed login attempts on your main web server from one IP address, followed immediately by one successful login from that same IP.
That looks like a brute force attack succeeding.
Exactly. Individually, those failed logins might be low-priority alerts, and the successful login looks normal. But correlated together, that's a high-priority security incident.
Or another example.
Maybe an alert comes from a server log showing a database administrator account running an unusual query. Then, almost simultaneously, a firewall log shows an abnormally large amount of data being transferred from that server's IP address to an external IP address somewhere else.
Working those together suggests data theft, data exfiltration.
Strongly suggests it. The SIEM provides that crucial context by correlating events across different systems that no single system could see on its own.
Indispensable for a modern security operations center, then.
Absolutely essential for visibility and effective response.
Finally, underpinning all of this is controlling who gets access to what in the first place. Identity and access management, IAM.
Fundamental. IAM is all about managing user identities and controlling their access to resources, applications, data, servers, even physical buildings.
The big benefit everyone talks about is single sign-on, SSO.
That's a huge usability win. Yes. Users log in once and get access to multiple applications without re-entering passwords. It reduces password fatigue for users and simplifies credential management for IT.
Makes sense. And what's the infrastructure behind IAM? How does it manage all those identities?
The sources point to three key components. First, you need authoritative sources. This is where the initial identity data comes from, typically an HR database for employees, for example.
Where the truth about a user resides.
Right. Second, there's the directory component. This is where the identities, credentials, and access policies are actually stored and managed, often uses standards like LDAP.
Like Active Directory or something similar.
Exactly. And third is the provisioning component. This is crucial. It handles the life cycle of access, granting the right permissions when someone joins or changes roles.
And critically, removing access promptly when they leave or their role changes. Deprovisioning is just as important as provisioning.
Absolutely vital to prevent orphaned accounts or lingering access privileges. And administration of this can be centralized, or it can be delegated out to different departments or managers for the users they're responsible for.
Okay, so we've covered a lot of ground today, from the proactive blocking of an IPS to the safe testing environment of a sandbox and this high-level correlation power of SIEM. Complex systems, all working together.
They are, and they're essential for dealing with external threats and sophisticated malware. But the sources also remind us where the biggest risks often lie today.
Not just outside anymore.
Increasingly, the focus is shifting to insider threats. Disgruntled employees, maybe someone just curious poking around where they shouldn't be, or even risks from outsourced service providers who have legitimate access.
That definitely complicates things, which leads to a final provocative thought for you, the listener, to ponder. If the major risk is internal,
Organizations need to start deploying tools like IDS internally, monitoring key network choke points inside the perimeter to track user activity, look for suspicious internal traffic patterns, and gather forensic data.
it gives you visibility into potential insider actions.
But it requires intense monitoring of your own employees' network activity. So the question becomes, how do you ethically and practically balance that need for internal security visibility against the equally important need to maintain employee privacy and trust?
That's a tough balancing act. Intense internal surveillance versus a trusting work environment.
It really is. And that tension between security visibility and workplace trust might just be the next major frontier in network defense.
Definitely something to think about for your own organization. That's all the time we have for this deep dive.